We're going to look at here a situation where we can have two possible triangles that are made. So it's a situation when we have something called angle side-side. So first of all, we need to recognize when we have an angle side-side situation. So what is angle side-side? Well, angle side-side is when we have an angle, and as we go around and find the other pieces of information, we go around the triangle here. We end up with an angle, then next to it is a side, and then as we go around the triangle there's no angle here, so the next piece of information that I run into is another side. So this situation is something we call angle side-side, and this leads to what we call the ambiguous case, or two possible triangles. So another way to identify when we have this is when we have an angle, an adjacent side, and a side opposite. Okay, that's often an angle side-side situation. So what is about this angle side-side situation that's problematic? Well, if we take a closer look at this side here, side 12, okay, is not fixed, does not have a fixed angle. So essentially, if I put a dot there, we can rotate that line of 12 into a different position. In fact, because of that length of that, it can actually take on this position here. Okay, make it a little bit better. It can take on this position here. That can be a length of 12. And what ends up happening then is there are two distinct possibilities for triangles given this angle, side, and side information. We can form this blue triangle here. We could also form this original triangle that I drew with the same angle, side, and side length. So we have to make sure that first of all we recognize when we have angle side side, and then we have to figure out, well, how do we calculate the different angles involved in here? Well, if I just label this B here, and we'll call this B prime, this angle here we'll call angle B1, and that's our acute angle, and the angle over here we'll call angle B2. Well, our calculator will always give us the acute angle, so it's going to give us this angle in here. So when we undo the sine, we're always going to get the acute angle, because the range or the output for arc sine is always going to be between negative 90 degrees and positive 90 degrees. Well, we can't get negative angles in triangles, so it's going to always give us the less than 90 degree angle here. We will never get this obtuse angle from our calculator. So I'll show you how this happens then. So as I set up my sine law, okay, I have an angle and I have an opposite side pairing. So I'm going to set this up using sine law. So I get sine of 65 degrees over 12 is equivalent to sine of angle B over the opposite side of 13. So there's my opposite angle pairing, and then I have my other opposite angle side pairing, and I have an expression which I can solve for angle B. So I'm going to cross multiply this to solve for angle B. I get sine B, and sine B works out to be 0.982 if I round this. Okay? And then as I do the arc sine on this to solve for angle B, arc sine, I have to bear in mind that my arc sine always gives me an acute angle. So it ends up giving me theta 1. So in this case, when I undo this, I get 79.06 degrees. So this angle in here is 79.06, and that kind of looks reasonable. Okay, it should be a little bit bigger than the 65 degrees because the opposite side is longer, so that looks reasonable. And it's certainly not going to be the obtuse angle that I drew here. Okay, so I have theta 1. Okay, I have my first acute angle, but how do I go about getting this other angle here? Okay, the obtuse angle. Okay, the obtuse angle can be found if we look at this relationship, we have the type of triangle that's made with this length of 12 and this other length of 12 here. This happens to be an isosceles triangle, which means that this angle in here must be 79.06 degrees. So what that means then is the relationship between theta 1 or B1 and B2 is that they are supplementary, or they add up to 180 degrees. So that's the key, that these two angles add up to 180 degrees. So when I solve for B2, angle B2 must be 180 degrees minus angle B1. I think I've seen this formula before, and if you think you have, that you're not mistaken, because this actually is a formula for theta 2 when we undo the sine in standard position. Okay, so this is the link between standard position and this triangle trig here, where we're solving for these non-right triangles. And really that's the only link that clear link that we have back to circle trig. Okay, otherwise we're really kind of doing two different things. We're solving for triangles, or we're doing standard positioning. So this formula happens to be exactly the same as what we get for theta 2. So the angle that I'm going to end up with here ends up being 100, basically 101 degrees, so 100.94 degrees. Okay, so this angle in here works out to be 100.94 degrees, and that looks about right. Okay, so that's going to be the acute angle. That is going to be the obtuse angle, which is supplementary to the acute angle that we found. So this is not from our calculator. So once we've established the shape, or worked out B1 and B2, we can solve this triangle. Okay, and this is what we end up doing. So I'm not going to complete this problem, but at this point we have two angles, two sides. We just need to find the third angle. Okay, so maybe I'll do that here. Okay, so this is going to be, we'll call it C2, angle C2. It's just found through adding up those angles to 180 degrees. So I do 180 minus 65 minus 100.94, and I get this small angle of 14.06 degrees. Okay. If I want to find the angle C1, which is this bigger angle in the yellow triangle, which I'll call angle C1, I would use the measurements here of the 79.06. So I do 180 minus the same 65 minus now 79.06, and I end up, this angle ends up being 35.94 degrees. So I have all three angles now. I have two sides. At this point we just need to solve for the final side here, and we can use the sine law to calculate the final length here using the two different angles. So we end up with two sets of information for the two different triangles. So I'll summarize it here. So we have angle A1, or A, which we'll call 65 degrees. Okay, angle B1 ended up being 79.06 degrees. Angle B2, and this is important to make sure that we separate this out, angle B2 was 100.94 degrees. Okay. Angle C2 worked out to be 14.06 degrees. Okay. And angle C1 worked out to 35.94 degrees. Okay, so we figured out all the parts that we need to. We're just missing now side C, and we would find side C using angle C1 here and angle C2 over here. We would get two different lengths for side C, because this one's shorter using the 14 degrees, and this one would be longer using the 35.94 degrees.